A very good morning to all of you. Today we have two sessions based on photovoltaic cells, introduction of batteries and hydrogen storage devices, followed by a tutorial session. So I welcome Pandey sir to present his lecture. Thank you. Over to Pandey sir.
Namaskar. Let's start. It's going to be a little easier day for us because there will not be any equations. But my idea is to sort of give you the introduction part of the energy related applications. We cover in the first lecture the photovoltaics, and then look into the water splitting and hydrogen storage. And in a sense, they are connected because the water splitting, the whole idea is to have a hydrogen fuel economy sort of related to it. And then we look into some of the requirements for hydrogen storage. And the next lecture is going to be on battery, what is out there. And especially I'll focus on lithium ion battery, looking into lithium sulfide materials characteristics. And I'll give you some results coming out of our group to show you that really the simulation models can help to improve the performance of a battery. Because we all know lithium-ion battery, the degradation is a big problem. And then I want to emphasize that the tutorial 4 is sort of very relevant tomorrow, which talks about electrochemical characterization, which is indeed related to photocatalyst water splitting, the chemistry.
मम्मी 3-4 रोटियां ही बनेंगी, उससे बहुत नहीं बनेगी।
अच्छा इतना हटा है 5-6 रोटी
तो देखो इसकी आधी बना दूंगी, आधा रख दूंगी।
इतना आटा रखा तो उसके 2 पराठे बने। फिर देखिए अभी मैंने तो इसमें इतना आटा है, तुम्हारे हिसाब से तो 6-7 रोटी बन जाएगी। आटा मिला दो, इसको आटा का रखना, वो बना देना।
खाना बन रहा है,
वो तो पराठे बना देना।
उनको बंद कर दिया। Wait, Dr. Naidu, can you mute your? Okay, so we are set. So let's do. Is okay now? So this again is what we are looking into, the solar energy conversion. And as you see in this slide on the first day is about solar energy. And we can tap into either thermal, chemical, lighting, or electricity. So you're converting the photons to electrons. And we have the photovoltaic materials to help expedite the conversion from photons to electrons. And this just gives you an idea about the number. If you look at the whole worldwide major population centers about the same latitude, then we can see indeed the power delivered by this radiation to Earth is about really pretty high. Is 1 kilowatt per square meter. So that's really impressive, which we need to tap in for future. And so this is again is to refresh sort of the concept, what exactly is happening in a photovoltaic cell. As you know, the photons sort of strikes the surface, and then because it contains the energy, is going to interact with the atoms, especially the atomic bonds, and from there, sort of again, because energy is quantized, So the ground states of our material, the electron gets excited to so-called the virtual orbitals or the conduction band and leaves the hole behind. So we have this electron hole pair. And we'll see there's another concept called excitons. So exciton is a particle where electron and hole, they are bound and they move in pairs. So one of the criteria for the material to be that we have to have this binding energy between electron and a hole to be very, very small. Then only we can utilize the material in a more efficient way. So the concept is exciton binding energy for a given material, which we definitely can get the information from either experiments or from simulations. So once you have the electron hole per generation, then we have the electron hole, they move because we already have applied the bias. So electron goes to so-called the N junction and the hole goes to the P junction. And once they reach the corners, we have the current is flowing. So the second most important thing is what is the mobility of these carriers in a given material? Because we had to have a faster mobility so that these carriers, when they move inside the lattice, they do not lose or they do not scatter out and go into what we call the traps in this sense. So the two things now is the exciton binding energy, and then what is the mobility? These are the two important factors in a given material. And then you have these, the terminal, then we have so-called the solar electricity. So just zoom in, and you can see here in a given solar cell, we have the front contact or the back contact where we collect the carriers. But there is also a very important part of this called anti-reflective coating. And that what it does is basically when the light or the photon gets scattered, then it does provide the further sort of coming inside, reflected back to material without hitting an electron in the solar cell. So this sort of improves the coating, the utilization of photons to generate these electron hole pairs. And that's really the must component of any given solar cell. So like I said, now we generate, or the photon generates electron hole pairs. So the question now is, can our material, can the photovoltaic material absorb the light? And as you know, we are trapping or sort of focusing on the visible spectrum of the light. So optical absorption of the photons in a given material is very, very important. And that's absorption is dictated by the band gap of the material. And we can get the information of the band gap either from both experiments or simulation. So in tomorrow's talk, I'll basically describe how to calculate the band gap and how accurate the band gap is. Because if you recall, yesterday, I think Dr. Naidu asked the question about the limitation of DFT. And this is one of the limitations of DFT, that it does not calculate or predict the very, very accurate band gap of the material. I'll go through the details and how to improve it. And second thing comes down to is the transport, which we need to know what is the mobility. And this mobility is, again, is can calculate from the effective mass, because we have the electron and holes as a free carrier, so they have the mass. But once they inside the material, they are being influenced by the periodic background potential of material. So that's why the term is effective mass. Their mass changes from free electron to effective, depending on the magnitude of this periodic potential, which depends on the chemical composition of the material, if you have ionic, covalent, or metallic bonds in that sense. So, like I said, then once we have this sorted out, then we can easily calculate the conductivity of the material, which in a sense is proportional to density of these the carriers, both electrons and holes in a given material. And this density depends on how well the material absorbs the visible light coming from the solar spectrum. So let's look at the carrier transport first. Like I said earlier, it's related to the effective mass of electrons. And if you look at the couple of formulas, and you can see here is we plotted a band diagram here of silicon carbide. And you can see on axis is our high symmetry points, and Y is the energy. So conventionally, in most of the figures, when you see 0, so 0 is designated as a top of the valence band. So all the bands of the levels, the below 0 are occupied by the electrons of a given material. And the bands or the levels above 0, they are all sort of a virtual or unoccupied state and forms a conduction band. So this effective mass, which is again is a, if you take an electron, so we have a free electron, which is, we know the mass is 1.6 in power minus 32, and then it experiences the effective potential because of the periodicity of the crystalline material becomes an M star. And this M star is, as you can see, is h cross square, which is a Planck's constant. And then we have a second derivative of energy with respect to the wave vector k. Because if you recall, we are talking about the k space, the reciprocal space of a given material in the first brilliant zone. So this second derivative means is what we are looking at, the curvature of the given band. So for this state, the top of the valence band, the curvature near the high symmetry points, which is gamma, is going to give us the value of the effective mass. And same thing, the conduction band also, the curvature provides the effective mass. So valence band becomes a hole, and this becomes a electron. And this is again is related to the mobility. If you look at the mu, the magnitude is nothing but E, which is electronic charge. The tau is a relaxation time. It's how much time this free carrier, either electron or hole, can move inside the lattice without being scattered, which is known again. You can get the information from either experiment or theory. And this more or less remains or depends on the bonding of a given material. And then we have the effective mass. So once we know the effective mass, the relaxation time, we can easily calculate the mobility. And tau being nearly constant in a given class of materials, what we can say, this carrier mobility or velocity is inversely proportional to the effective mass. So that's a very important parameter to characterize material before we can apply for solar energy applications as a photovoltaic material. So you can see here, smaller the curvature, is going to be heavier mass, and if you have the larger curvature, is going to be a lighter mass because of the inverse relationship. So let's move to the materials. And it's a long history of materials, especially the solar cells coming from this photovoltaic effect. And so we classify in called different generations. So the first generation material, which probably you may know, basically based on either the crystalline, the mono we call crystalline, or a polycrystalline silicon. And later the gallium arsenide came into the picture. So the silicon technology as we know, is well established. It has been around for almost 50 years. So it's very easy to integrate these materials on a silicon technology platform. So they tend to be low cost, but I'll show you the problem is it leads to a moderate yields in terms of the efficiency. Then we moved to a second generation, almost about 30 years ago. So instead of using a single crystal silicon or silicon powder, we moved to thin film technology. And here, so-called the chalcogenides, remember the cadmium telluride sort of came in as a very good material, and especially thin film is easily can be made from a lab to manufacturing industrial scale, but it does have a lower efficiency. Then we move to so-called the third and fourth generation currently. So these third and fourth generations are I call it in the lab scale, still not in the production mode. So one can use a novel materials, basically the 2D materials or carbon nanotubes combination. So they tend to be expensive, but definitely the efficiency goes way, way high, it's about more than 40%. So there is still a trade-off between efficiency and how expensive the material is. The fourth one is coming in, which is again is very promising because of being a low cost. So what it does is it takes the polymer thin films, and then you make a composite, which you can combine with the so-called the nanostructures. So they could be the quantum dots of the metal or metal oxides, or you can move to the carbon-based materials. So it's a composite of polymer thin film, which is a host, and then we add these quantum dots or graphene flakes to improve the efficiency. So being a polymer is a really low cost in terms of manufacturing. It does provide the flexibility, but it's still both third and fourth generation are being explored for scaling up processes. So let's look at the numbers now. As we move down, look at the single crystal monosilicon, or we have polycrystalline silicon. You can see is still hovering around about 20% efficiency. Then we move to the second generation, the thin films of cadmium telluride, which you can use easily the deposition techniques, and this is still about 21%. And third and fourth generation is quantum dots. Again, are the other nanomaterials. They're easy to make. They are a very, very efficient conductor, but again, you can see is little less than what we have in the first generation, which are being manufactured. And then we have the fourth generation coming out, which again is trying to improve the efficiency. So it's a low cost because it's solution based. And definitely the electron transport conductivity is much better compared to other cases. But as like I said earlier, they are still in labs. So let's look at the timeline. Sort of gives you historical perspective that back in 70s or early 80s, we had the silicon, first generation. And then we moved to so-called the amorphous silicon, which is passivated by hydrogen. So you can move from the crystalline or polycrystalline sample to now thin film. And the cadmium telluride also came in mid 80s. And then we moved to so-called the different kind of cells, DSSSC, which is the organic based sort of a supercell. And then we have the fourth generation, we call it, is a combination of different materials. You can see here is a photovoltaic, the film with the CNT and quantum dots. Here we have zinc oxide, and then so on. So there are definitely is progress is being made in terms of the cost, manufacturing cost, and the efficiency. So let's look at some numbers. Silicon. So this is again is I call the back of the envelope calculation, because in my career I realized is one has to be really look at the numbers before we look into the materials properties. What kind of numbers we are talking about before we can understand either their property or their applications. So if do some calculation depending on the Avogadro's number and how many valence electrons you have, you can easily see they have a very large number of electrons per cubic millimeter of a silicon wafer or a silicon sample. But what happens is because of the band gap of the material, we had to have very high thickness of silicon to get a good solar visible light absorbance. That's the key thing here. So we do have a lot of a density of electrons, a carrier, but absorption is poor because we need a thick film to get it absorbed. So theoretically, one can sort of calculate what is the ideal limit of a given material, which comes from the absorbance, which is related to the band gap. And this is called Shockley-Quezier efficiency limit. So for a silicon, which is a band gap of 1.1 eV, the limit is about 32%. So, and we are hovering about 20-24%. So this is not bad, because even if you go to the maximum absorbance, you got to have a band gap of about 1.34 eV, which again provides about the 40% efficiency in terms of the absorbance. So this ideal limit, and but again, as we know, once we make the sample and the solar cell, we have a lot of other, I call secondary factors kick in, which reduces the efficiency. And the first thing is once we generate these electrons and holes in the material, instead of again going to the anode or cathode, they recombine. So the recombination of charge carrier is one of the secondary factor which degrades the performance of the sample. Then depends on the conductivity, and then reflection again, which we try to take care of by anti-reflection coatings and other small effects they kick in, defects or dislocations and so on, which reduces the ideal or theoretical efficiency for a given material. So this is again a cartoon, how gives you an idea what kind of a manufacturing process we are talking about, which is not easy. You can see there are really is a lot of steps are involved. Especially, I give the example of these photovoltaic silicon-based cells. Advantage what we have is we have the well-established platform coming from the microelectronic devices, including circuits or transistor, which are silicon-based. So what we do is we start, if you look at the process here in any sort of production facility, you got to choose the substrate where you're going to deposit it. And this substrate tends to be an insulating layer, because what happens is once you generate in this active layer, which is the material we have, if you generate these electron and holes, if you don't have the insulating layer, they tend to leak out. And that again, leaking out of these carriers means you are reducing your efficiency. So once you have the insulating layer, what we do is basically you then deposit the back contact and the reflector. Once you have this thing, then you do the active layer, which is over the material. Then you have the conducting layer, which tends to be the transparent conducting oxide. Mostly the tin oxide layer comes in, and then you do the other part about the corrections and another layer of the insulator, and then you encapsulate the whole device. So it's a lot of steps. It takes time, but ultimately you have the so-called solar cell based on silicon photovoltaic material. So this again gives you an idea about what we are talking about in terms of the technology, because as I said earlier, we need a very thick sample. about in 180 micron for these the silicon-based solar cells. But as we move to cadmium telluride, you look at the drastic reduction. Is about a 3 micron film is sufficient. So you can see here is the difference comes mainly about the absorbance. That silicon band gap is a little smaller than what one needs to have it, and that's why it has you need to have a larger thick sample to absorb photons, which you can get away by using cadmium telluride thin films with only 3 micron thickness. And once we move to this combination in organic, the quantum dot based, we are talking about really a few tenths of micron. And you can see, and just to an idea, our hair is about 100 micron diameter, and our red blood cell is about 7 micron diameter. So the manufacturing process has to be very, very refined in order to make such a small thin films for solar cell applications. So sort of gives an idea, it's not easy to manufacture these quantum dot based solar cells, because scaling up from lab to industrial scale is really complex because of the size. So let's look at the quantum dot. The advantage what we have is we can tune the band gap. As I said earlier, if you pick up the say cadmium sulfide quantum dot, and the absorbance or the transition is basically depends on the diameter of the dot. So it is inversely proportional to the diameter of the dot. And this fact comes from that because of the so-called the quantum confinement effects, which takes away from the bulk-like behavior to the size-dependent band gap. That's the key thing here. The quantum confinement effect gives us a tool to tailor the band gap, whatever the wavelength we would like to have in our material. And on the right, you can see, if you look at the wavelength versus the absorbance, depending on the diameter. If I look at the black line, this is a 3.7 nanometer diameter, and simply be reduced by 1/3 to about 2.3 nanometer diameter in blue. You can see there's a significant shift in the absorbance speed, going from around 620 to about 520 nanometer. So that's a very sort of important for us to tailor these absorbance speeds depending on what we would like to have it. That's a big plus. So let's move to now second topic. But before I do it, any questions, comments about these photovoltaics? No? Okay. So let's see what else can we do. So I move to the second part is photocatalyst materials. And there again is coming up because we can use them to produce hydrogen. And as we know, the hydrogen really is a very, very clean fuel. And if we can do it using the solar energy, we are in a good shape. We don't need anything else. So what it does is water splitting. Is again a simple equation. Is H2O goes to H2 and O2. But if you look at the process here, is pretty high. The barrier is pretty high. It's about 237 kilojoule per mole, which is about 2.5 2.3 eV. So it's not easy to have water split into either hydrogen or oxygen. So what one uses is so-called the semiconductor catalyst. So what it does is it simply reduces the barrier. And once you can do it, then is really we have a hydrogen available for the use in these energy applications. And it gives you an idea also that if you do this splitting of water, 1 liter of water, it takes an enormous amount of power. It's about 4.4 kilowatt hour. So that's a pretty large number. So these materials kick in now, the photocatalyst materials, which sort of provides a lower barrier and of course the lower power or the energy requirement. So what happens? So this is again introducing the so-called the terminology, or giving you sort of an overall idea. I'm not going to go in details about the chemistry of the material, but this cartoon basically, it tells you is we are looking at is the neutral water, pH is equal to 7. Because the whole process, as being in chemist, if you're a chemist, you know, is a pH dependent. Either we are going to alkaline or acidic behavior, and then changes completely the requirements of the energy and the efficiency of the process. So in a typical way we have is the photocatalyst material, which you can say is VB is our valence band, which is the occupied. And this is the conduction band, which is the unoccupied. The photon comes in, and depending on the gap, it absorbs the photon, this material. Once absorbs, energy is here, the electron sitting in the valence band moves up to the conduction band. And so it leaves behind the hole. So we have this electron hole pair, what I refer to exciton. So key thing is what is the binding energy of this exciton? It has to be very, very low so that they can sort of move or split away from each other. So the electron migrates to this side, what we call is a hydrogen evolution side. Okay, from converting H plus to H2. And this reaction is typically, as an acronym, is there called HER, which is a hydrogen evolution reaction. So the important parameter for this catalyst material is how well they can provide this HER reaction or facilitate HER reaction for the generation of H plus to H2. Now, on the other side, the whole moves to so-called the oxygen evolution side. And this is known as OER, oxygen evolution reaction. And in this sense here is water basically is being converted to O2. So both HER and OER represents so-called the reduction and oxidation of water on the surface of this photocatalytic material. So what kind of properties are involved if you would like to have the good sort of efficient water splitting so that we can have the hydrogen production? So the first thing we talk about, the band gap or the absorption, because I see from this cartoon, the photon has to be larger than gap, then only it can excite the electron, making electron hole pair in this material. If the gap is smaller than the incoming wavelength of the photon, nothing happens, just scatters around. Is there any question from chat? Oh, hi, Ayushi. Yeah, that's I'm going to go through it. This slide. And important thing, like you mentioned, is a semiconductor. why do we have to have a semiconductor? And you can see the answer in this slide, because semiconductor has a gap. And if we remember the solar spectrum, we are looking at only the visible part of the solar spectrum. And the peak is around the yellow, called 550, 520 nanometer, so which relates to about 1.33, 1.34 of the band gap. If you take the metallic system, metal does not have any gap. If you take an insulator, like oxide, they have very large gap, about 4 to 5 electron volts. And as you know, if our photon energy is less than the gap, photon is not going to get absorbed efficiently. And then it cannot create this electron hole pair, which are necessary for HER or OER reactions. Does it answer your question? I cannot see the chat.
Mr. Someshwar Rao?
Hello, madam.
Yes, sir. Please continue, sir. Do you
Yeah,
have
go
a
ahead,
question,
please.
sir?
I have first one question, madam, regarding photovoltaics. Hello?
Yes, sir. Please continue, sir. You're audible, perfectly audible, sir.
Among all these photovoltaics, silicon, platinum, and quantum, which one has more efficiency, sir?
Sir, please repeat, sir.
Can you write on chat?
Or write in chat, sir.
Among all these photovoltaics, which one has more efficiency, sir?
Oh, okay. I'm going to come through the slide. So I'll show you the next slide.
Yes, sir. Yes, sir. Okay, sir.
Yes. This is just giving an idea, concepts, and then later on we will talk about more on day 5 when we talk about the future and the challenges. Is what is the state of the art is. But I'll show you some of the slides in just giving an idea. I'll address your comment later. Is okay? So, so like I said, there are a lot of factors are kicking in a materials property. And so first thing is the light gets absorbed, so you have band gap, proper band gap of the material. But second most important thing also is the called formation of exciton, electron hole pair. So what we need to have, this binding energy has to be very, very small in order to electron can go to HER side and hole can come to OER side. So on the right, you can see the binding energy of this pair is being calculated. And you can see from here, these are the 2D materials. And if I pick up, say, MOS2 or WS2, they have such a large binding energy. Because light gets absorbed, we have the electron hole formation. Now they are bound by, say, electron volt. So in a sense, we had to again provide more energy to break this electron hole pair bond so that they can move to their respective sites. Related to, if I look at the, say, tin selenide, or the new materials called lithium gallium sulfide, where we have the half of the binding energy. So as a industrial person or synthesis person who wants to make these photocrets material, they're going to prefer the low exciton binding energy materials related to the high binding energy materials. So this is one of the factors. Second factor which comes out, we talked about in photovoltaic also, how fast these electron holes can move through the lattice. So the mobility becomes important. And then we have furthermore factors coming from the reaction rate, is what is the catalytic efficiency, or what is the transfer of the reactants and products. But that can be, again, taken care of by the chemist. As a physicist or a simulation, basically we focus on these three things: the band gap, the binding energy, and the mobility. And just like I said here is smaller the value of this binding energy, is going to be much easier for the exciton to be separated in electron and holes. So this is again maybe answering this question about the efficiency. So what they use is this sort of if you remember, and the photovoltaics, we are talking about the power density or energy density of the material. But here we have so-called the solar to hydrogen efficiency. Like we bring the photon and we produce hydrogen. And this is again is given by equation where we have the photocurrent density J and then a power density P with some number called 1.23 eV. So this is sort of a standard formula to calculate the efficiency of the material. And you can see this slide is efficiency is again hovering around about 30%. And always remember, this is all the lab work, is not here the market, the manufactured, the numbers. So you go from a zinc selenide, which is very, very poorly in terms of the efficiency is about 4% compared to in between, and the combination of the lead palladium diselenide, which I'll talk to you about this work on hopefully day 4 or day 5. We had done some simulation to look at the water splitting on PdSe2. We have so-called the incoming material, tungsten sulfide selenides, a combination called Janus hydrostructure with about 10% efficiency. And finally, we have the palladium-based sort of compounds reaching about 28 to 30% efficiency. And always remember is for a catalyst, the palladium is a well-known catalyst. So it helps to improve not in some of the materials property, but this efficiency or the mass transfer of the reactant products in palladium-based compounds is excellent. That's why they are way up in this this chart. So let's move to now. What exactly is going on? And I'm not chemist. I'm coming from physics side, but I think as Dr. Bhavna Singh has prepared a very nice tutorial, which is going to be tomorrow on electrochemistry. So I'm going to give you some kind of introduce you to the words. And the first word you're going to hear about the redox reaction, which is again going from H2O to H2 and O2, but in different steps, reduction and oxidation. But also we have a word called over potential. And it's very common to this terminology in electrochemistry. So what it does is this over potential term basically provides a kind of a measure or degree of a barrier, in kinetic barrier, which is when H2O is being split to H2 and O2, you see the barrier is about 270 kilojoule per mole. So this barrier can be measured by noticing or looking into the over potential term. And lower the over potential term or the barrier is, we are going to have a higher efficiency of a cell. Like we talked about it, there's a minimum voltage we need to have to split water into hydrogen oxygen, which is about 1.23 at 25 degrees Celsius. And this should be 7, not 0 at neutral water. But as we know, as we make the samples or do the measurements in our real world, we cannot reach the theoretical limit. Always going to be higher because of the kinetic factors and so on related to the both HER and OER reactions. So this is further. And either if you're an engineer or a physicist, the terminology is a little what I call the awkward. Is they call is half cell reactions. So the first half cell is a HER, where we have the H2, and the second one is the OER, where we produce the O2. So, like I said earlier, is the role of this catalyst is to minimize the over potential so that we can have the efficient production of H2 and O2. And this catalyst is, of course, physics tells us It got to have good band gap and low exciton of binding energy, but the chemist says also got to have a low over potential. So you have a lot of factors coming in before you can decide which material is going to be the appropriate material for highly efficient water splitting. So you can see here is I think our job as a faculty or a student is to provide a database for the industry or the manufacturing scientist. So instead of doing the trial and error measurements, what we can provide, say, pick only the few of the materials which has a good band gap, low binding energy, but also the lower over potential values. And this again gives you what I've been sort of talking about in a chemistry term. Is they're talking about now the free energy and so-called the reduction potential and the oxidation potential. And depending on these potential terms and the free energy, it sort of relates to the chemistry part of the efficiency or to measure the efficiency of a given system. I'll not go in detail here, but it's well known in chemistry books. So I think the question was about the catalyst, and you can see this is a very nice cartoon. If you look at the reaction from H2O to H2O2, the black is without the assistance of catalyst. So we have the ground state, and the barrier comes in, and you have the transition state when it splits, and then you have the hydrogen and oxygen, and this is the barrier. But you can see once you have the catalyst, then you really reduce this barrier significantly. So the rate of reaction really goes at a very higher value, a larger value compared to without catalyst. And this is always going to be an uphill reaction in chemistry term. Otherwise, we would be sort of generating hydrogen without any efforts from water. How much time do I have? I think I'll skip this slide. Okay, so I'll skip this slide and then move to the question is, okay, now we have the hydrogen. What do we do with it? So the next step is think about the storage of hydrogen. This is again the normal slide, but the key thing comes down to is hydrogen is gaseous at ambient temperature. I'll go a little longer this time and have shortened the next talk. Is it okay with you? So because of the gaseous nature, definitely is going to be a problem in storing it. And as we know, advantage is it really packs the highest energy per unit mass of any element in the periodic table. And of course, is renewable and is available on Earth. So if you talk about, this is the buzzword called hydrogen economy, is two steps. One thing is how to generate it through the water splitting because of the photocatalyst, but then also kicks in the storage, how to store this gas, hydrogen gas, because once we know how to store it, then definitely we can use for electricity generation or so-called the fuel cells. So storage is also is one of the challenges before we move forward with the so-called the hydrogen economy. These are some of the sort of efforts have been going on that even if you do at a high pressure gas storage, say 10,000 psi, look at the energy content here. As you have 4.4 mJ joules, such a large number per liter. And if you look at the fossil fuel, is about 30.1.6. So efforts have been going on. This is a slide, if I remember, from Netherlands. They are sort of trying to use this compressed gas cylinder at pressure for the bus systems. But this is not practical. I think this is also just to show that one can use hydrogen fuel to run the buses. But again, is we have to compress it, means we are talking about here the cost. And then, of course, the leakage, they are too heavy, and these cells are still too expensive. So if I look at it here, again, these are some numbers. And from hydrogen to liquid storage, what is the density of liquid? What kind of energy content is going to have it? And then, if you look at the challenges, is definitely is not easy, or low cost liquefaction is not available, because a large amount of energy is needed to liquefy the gaseous hydrogen. And then again, you need to go, it's well below the room temperature, is about 20 Kelvin to do the liquefaction. And then you have a lot of technical issues. So let's do the alternative route. We cannot look into the liquefaction of hydrogen gas. Can we store hydrogen in materials? And here I'll give you, again, is next 5 minutes, what kind of materials and how can we use them. So this is, again, is a cartoon. And we talked about this liquefaction and storage to compression also. But some of the materials are coming in. Is the magnesium hydride. These are called the borohydrides. These are called metal organic frameworks. Or so also we can use the porous materials. So idea is basically the hydrogen comes in and gets attached to these materials. But the key thing is, always remember, is we can attach them, store them. But this binding of hydrogen to the material also be very, very weak, so that we can decouple the hydrogen attached materials into the hydrogen fuel. So it's easy to attach it, but the question is, can we also detach it? Associate dissociation process becomes very important. So we can define some kind of criteria coming out. And first and foremost criteria is this binding energy. Hydrogen with the material has to be very, very small. It's a few tens of electron volt. And of course, then you have the other criteria. But from materials point of view, this is one of the foremost criteria. So like I said, the hydrogen comes in because it's binding energy value. It depends on does hydrogen physisorb on a material or chemisorb on a material. And as a scientist, physicist, or chemist, we know physisorption is always a weaker related to chemisorbed materials, which has a very strong binding. So we are going to prefer the physisorption of hydrogen on these novel materials. And this is a couple of slides which sort of shows what we can do using simulation. So we have, again, this is a cartoon of a nanomaterial. And what you do is you bring in this hydrogen molecule and then see, does it get attached, on which side is going to get attached, and how many hydrogens are going to get attached. So you always calculate the equilibrium configuration of this hydrogen adsorbed on a quantum dot. In this case, you can see here so let me go back. So this is physisorb, but what happens here, because of the reactivity of the quantum dot is sort of dissociates into 2 hydrogen atoms at different sites. And here some gives the numbers about it, is how far and what the kind of the binding energy you have to look at it. So just like I said, physisorb process has a binding energy about say 0.76 eV. It's really the weaker bonding because it's far away from the lattice side. But if you look at the chemisorption, it's the higher binding energy, and also is a much smaller distance from the quantum dot. So these are again is what I call is a filter to experimentalists to let them know that this particular quantum dot, is it going to physisorb or chemisorb the hydrogen molecule? And as we know, physisorb has a smaller binding energy, then that quantum dot is going to be preferred over the other quantum dots for further investigations. So again, is a lot of proposals are coming up. Is metal hydrides, but the problem here is that they have the strong hydrogen binding. Then we have the nanostructures, or I call the porous materials, including the metal organic frameworks, and both have the weak hydrogen bonding. So in a sense, is preferred material, if you ask me, are going to be nanostructures or porous materials related to metal hydrides. And this gives you again is an idea about what kind of weak binding we are talking about. So what you can do, you can look into this slide here, and these are coming from the simulation work, that a C60 molecule can absorb so many hydrogens. So you can see here that scandium 12 C60, it can store hydrogen up to 8.88%. And then if you reverse the process, is going to be 7.08%. That's a pretty big amount actually in terms of the storage. And that's a promising. But again, this is sort of a lab scale results. If you move from scandium to other transition metals, from titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and you can see here is if I'm plotting here the binding energy with the different sides, and as you move up to higher transition metal elements, you can see the binding energy goes up. So like I said earlier, is our expectation for it to be hydrogen storage material going to be a weaker binding with hydrogen. So what it comes down to is indeed only the early transition metal elements are promising related to the higher ones, the later ones. And they can up to, you can see the different graphs, the 1, 2, 3, 4, or up to the 5 hydrogen molecules can be absorbed and bound by scandium with a binding energy about 0.3 eV. If you go to nickel side, it can only take about the 2 hydrogens related to scandium. This is a similar sort of cartoon. You do and look at the side and the different sort of buckyballs doped with transition metal elements, and you find ultimately is really this compound can absorb so many hydrogen molecules, and the binding energy is again remains about 0.5 eV per hydrogen. And again, it shows the early transition metal, which are being sort of introduced into C60. They have a really remarkable hydrogen storage properties. Now move to CNTs. Same thing here. What you do is you take the CNT, bring in one H2, calculate the binding energy, bring in second, third, and fourth, till we find the binding is not possible. And when you do, again, is you look at the numbers, it's coming about 0.2 electron volts per hydrogen. And look at the weight percentage here. It's pretty high, it's about 7.7% in doing it. But the key thing also, see, that's the advantage with our simulation, that you can play around with different numbers. So this is the one titanium atom. What we can see here is as we increase the titanium atoms in the carbon nanotubes, which is decorated with it, we can definitely decrease the binding energy going from, say, 4 titanium to 8 titanium. So it goes down from 0.4 to 0.18, which is really preferred. You have a higher storage, but the weaker binding. Same slide is different, and you can see once we again go further, more and more titanium, so there is a limit always. What happens is going to form so-called the titanium clusters. The aggregation becomes a problem in metal atoms, and then in turn it reduces our intake about 7 weight percent to about 3 weight percent. So this again you have to find a balance about how many transitional metal atoms can be decorated on a given carbon nanotube to have a efficient the hydrogen uptake. Now we move to also the lithium, and more or less same sort of stories is here, that you can have a more and more hydrogen when you decorate with the fullerene, not the nanotube. And then if you have more number of lithium, you're talking about here the lithium 12C60 decoration. You can see that's your intake is become 13 weight percent. Binding energy is very, very small. This is what you would like to have. And there are reasons. I'm not going to the reasons why lithium is better than transitional metal atoms for this case. This is again another cartoon is called a metal organic frameworks, and you can start again attaching the hydrogens. And if you look at the intake is still low, about 1% at room temperature, but once you reduce the temperature, it goes to about 5%. And this is again the preferred mode of absorption is a physisorption. That's a plus point. So let's give a summary. Is the hydrogen storage? Definitely we can look into the metal decorated, both fullerenes and carbon nanotubes, or even a graphene. But like I said earlier, is once we have the more number of metal atoms, they tend to aggregate and form a cluster. So this is the one has to be aware of it. And then it's coming out is the organometallic complexes, especially metallocarbanes or carboboranes, which can be considered for the hydrogen storage. And this is the last slide, if I remember. This is again is coming from simulation, and here they have moved away from either transitional metal or lithium to so-called the alane clusters, which are clusters of simply Al with the hydrogen. And they used sort of a trizene-based framework, which is again is a porous, and they are decorated with the ALX HY clusters and looking into the hydrogen absorption, which is again is a promising case in the lab. This is the last one. You can see here is a porous again. We have the lithium nitride, and then again you can see the gray spheres sort of hydrogens coming in and being absorbed on lithium nitride, which is further embedded in the porous structure. So what I see is the future about hydrogen storage material is you're going to have a so-called the porous template or porous substrate. You embed with either metal decorated, lithium or transitional metals, or you look into some compounds like lithium nitride, which can physisorb these hydrogen molecules, providing you the higher weight percent. Good, so I think I'm done. So I think floor is open for questions, comments. So just to summarize, is photovoltaic material, we talk about the band gap, the transport, which is the carrier transport. We come to the hydrogen economy, hydrogen fuel storage. We need to do the photocatalyst, which needs to again tune the band gap. But we also have to take care of the exciton binding energy, as well as the chemical aspect of the reaction we call HER, hydrogen evolution reaction, or OER, oxygen evolution reaction. And finally, we looked into, once we generate these hydrogen, then where to store it. So typical way is to compress it or liquefied it, but again, it's very, very expensive. We looked into some of the materials, and the criteria is the binding of these materials with hydrogen needs to be very, very weak. So the preference is going to be physisorbed hydrogen on these materials as one of the criteria to move forward. Dr. Naidu, I'll give you in the second talk some of the software packages, but these results are, if you're aware of it, using a lot of software packages, because depending on the tool, kind of material I'm looking into it, or our group is looking into it, is either used called WASP or a quantum espresso, but for such large one is we look into the called CSL or a crystal program. But I'll give you the list after the second talk. Is that okay, Dr. Naidu?
Any questions from the audience?
But you can see, I think is my idea is to give you is field is still open. And if you have a very good idea, or we would like to look into the different materials properties, they rightly fit in either both from experiment or theory to generate this the database. Because still both third and fourth generation materials are in progress, not yet for the production. Good, so we'll take a break, 10 minutes or 15 minutes.
15-minute break. Please be ready.
Let's
for
make
the
it
group
15 minutes.
15 minutes.
So 11:40. 20 minutes.
20 minutes break.
Because next talk is going to be a little smaller. So let's meet at noon.
Before that, please join the video for the group attendance and group photo. 20 minutes break.
It's good to see the faces actually. Morning, Aishi. Oh, you're fixing it.
Yes.
It's okay, you can cut me out.
Yes, okay. ऐसे ही हो गया थोड़ा little bit
Need some.
बस okay stand
It's okay, I know.
Thank you very much. You may stop your video, please. Much. sir, which material is more visible in terms of economic purpose?
If you ask me, still silicon.
Silicon.
Because technology is out there. And as you know, the companies, they don't care about the efficiency, they care about the cost.
Okay.
And I didn't give you the numbers, but silicon is very cheap. It's there, on Earth, especially amorphous silicon. But the big problem is the degradation. You make it in a few rupees,
breakfast and transportation.
Sorry, I got to go start again because I was told I was talking to myself for the last few minutes. So what you're looking at is if someone asks a small child is what exactly a video is not start. Good to go? Come on, you are a production assistant, you know, you should say. Okay. So simple answer for a little kid question is what the battery is. We definitely say is simply the conversion of chemical energy, which is stored in a battery, and then we convert it to electrical energy. And if you recall the old lead batteries, what we have is the anode, cathode, and the liquid, which tends to be acid, remember, and we have to be very careful dealing the lead batteries. But now the push is towards move the solid electrolyte. And the key thing is going to be because, as we know, electrolyte facilitates the migration of these ions. Remember, we are moving away from electron and hole, but we are not talking about the ions in these migration. So these electrolytes, they are solid state. They have to have a property called very good ionic conductors. Then only we can use in a next generation battery system. That's one of the key criteria of solid electrolyte being a good ionic conductors. So I'll show you some examples and then move to a lithium-ion battery system, which is as we know is coming up everywhere, and thanks to Tesla, it's being used in automobiles in a big way. And then I'll show you some of the recent results from our group from simulation, not how does we can improve the aging process in these battery system. So our idea is to look into the reason why does the battery degrade, and then once we know the reason or once we understand it, then we can improve the self-life of this battery. So this is again is a cartoon. You can see it's we have as a solid electrolyte battery. So you have the contacts, the anode and cathode, and this is we have instead of a liquid we have the solid system here. So if you further zoom in, what we are looking at is a component, the anode component, and then these metal ion batteries, they tend to be a graphite or silicon or a titanate or lithium metal if we have the lithium ion battery. So that's our anode. If you look at the cathode, these are again the transition metal oxides is a well-known lithium cobalt oxide or spinel structure, lithium manganese, or olivine structure, lithium iron phosphate. So these form the anode and cathode. And in the middle, what we have is this solid electrolyte, not the liquid, the solid one. And a lot of crystalline materials have been proposed. LGPS, there are a lot of acronyms, but I have added the chemical formulas also. Or garnet crystals, or antiperovskites, or argyrodite, basically a combination of lithium, phosphorus, sulfur, and fluorine, which I'll show you some slides. Or we have the antimony-based antimonate, and so on. So what's the advantage or disadvantage we have over liquid versus solid? As we know, we have pros and cons. And liquid is, as we know, is conductivity is very, very high. Boom, the ions just cross from anode to cathode very, very fast. But as we also know, the cons is they tend to get overheated. So boom, they explode, and you have this danger coming from the hydrogen gas explosion or other gases they come out. The solid is of course, if there's no liquid, then it's going to be safe and pretty flexible. But again, the cons is their conductivity is not as good as a liquid in most of the cases. And here you have the sort of the cartoon coming from anode to cathode. What we use here, either liquid or solid electrolyte. So, as I said earlier, is one of the criteria for a material to be a good solid electrolyte, and it has to have a very high ionic conductivity. And in terms of the number we are talking about, 10 power minus 3 unit of the conductivity per centimeter. Then, once you have the high conductivity, but also we have to have a low activation energy. What it means is if metal ions, say lithium, is crossing this electrolyte, they should not bind this metal ion. So in a sense, at room temperature, of course, they're going to have some reaction, but that reaction is going to be a weak binding, so that at room temperature, these metal ions are mobile. And then, of course, you have the stability, which is basically defined by either the phase of the solid, and then is about the band gap, because as we know, they're going to bombard it with the photons. And so what kind of band gap do these materials, which you would like to avoid the absorption of photons, so that they are not get degraded. So it's totally reverse of what we have in photovoltaic and photocatalytic materials. And then, of course, you have the other properties I call the secondary factors coming out, is what they call is this dendrite growth of lithium metal anode, or what kind of interface is there, and then can we make a good contact with both anode and cathode of these solid electrolytes. Remember, we're talking about the solid state part, not the liquid part, because the liquid part, this sort of does not matter. And like I said earlier, is the conductivity is the major issue about these materials. So this is again is one of the materials being considered is called perovskites or antiperovskites. So they have a structure called ABX3 or A3BX, where A and B are cations and X tend to be anions. And you can see here is pretty flexible. So you have structural flexibility. And again, we need to have a structural flexibility, because these are lithium or metal ions, as they are migrating through the electrolyte, they have to have a space to get it through. And that's why they are going to have a high ionic conductivity. Then, of course, they're going to have a phase stabilization. And over the years, people have come up with some kind of empirical formula, what they call a tolerance factor. And this tolerance factor comes from the geometrical consideration. It's nothing about the composition. It's simply the structure of the material. And what it tells is the factor has to be sort of a dependence on the radius of these individual constituents ions of a given material. Ra plus Rx divided by square root of 2 Rb plus Rx. And that's what it defines that they are either appropriate for being chosen for a solid electrolyte or not. This again compound is now it's a lithium based. It's called argyrodite, but stated simply is the Li6P-S5X. Now here is X is a cluster. That's again coming from simulation from Dr. Jenna's group at Virginia, and he's looking at the structural flexibility as well as the cluster, which sort of can provide the diffusion part that's coming out, the conductivity. And you can see here is conductivity is definitely the order of the number which you are looking for, 10 power minus 3, because 100 ms per centimeter. But the good progress is being made in terms of the activation energy, because these materials, they are so flexible or so porous that if the metal ion compared to the lithium comes in, and it needs a very little energy to go from one side to the other side to the anode. So I think there's two things which I want to emphasize about the solid electrolyte. First thing is the high ionic conductivity. And second thing is structural flexibility. That's the two thing, which is sort of necessary for the material to be solid electrolyte. Let's now move to a lithium-ion battery. And as we know, they charge fast. You look at your phone and boom, it's sort of gets in few hours. They last longer, and they have a high power density compared to other systems. They do have energy storage and release, and that's the whole process. What we have in a battery is coming out of this movements of lithium ions from positive to negative, charging and discharging back via through this electrolyte. So we talked about liquid electrolytes instead of a way back in lead batteries we had the acid, but now they have called lithium salts, especially lithium iron phosphate, which can be easily dissolved in an organic solvent like ethylene carbonate. So the whole idea about this electrolyte is it acts as a conductive pathways, going from charging discharging process to facilitate the movement of ions. But we also do have in terms of the electrode, so we pick up a positive as one of the lithium source, and negative is the host for the lithium which is coming in from the positive electrode cathode. So let's look into our interest now is the research wise. We thought let's look into the lithium sulfur system and see what is out there. So in terms of the energy density, it's pretty high. We are talking about in terms of the kilos, it's about 300 to 600 watt-hour per kg. Is a normal one, and we are looking at for lithium sulfur is about almost 10 times. You can see order of magnitude difference. If you look at the cost, is pretty small compared to the nickel cadmium or nickel cobalt batteries. Is the per ton, if you look into the US dollars, is sulfur, which is required for lithium sulfur batteries, is almost nothing. We're talking about a few $1,000 per ton, and cis sulfur is only the $50 per ton. And of course, we have the lower environmental impact. This is a good thing, and as you know, every good thing has the bad things also coming up together because this is the whole package. And the problem is conductivity is low, especially. There is also, which we'll talk about, there's a variation in the volume of the cathode, and it goes up to 70%. And that's a really is no for the performance of the battery over time. And then you have so-called this diffusion problem and structural effect, which I'll show you we have tried to address coming from the simulations. So this is a cartoon. It's just to give an idea about where we are in lithium sulfide battery. So this is called energy density, and thus we have the volumetric energy density. So basically, we are looking at the specific energy versus volume energy density curves. And way down here is our old lead acid battery. Then we move up to so-called the nickel cadmium and nickel MH hydride batteries. So you can see here is if you go up in this scale, is this smaller cell size, and if you go up here, we have the lighter weight. So you have to sort of find a combination. So lead battery, if you remember, I asked the parents, they tend to be very, very heavy.
So it's big and heavy. We move to now this area, which is again is a lighter and smaller. But look at here, is we're talking about the lithium sulfide is coming out. Indeed is a light and size is also small, giving a very, very nice performance. And down the road, of course, we got to have some expectations that is going to go this way if we address some of the issues about the degradation. So this is again is repetitive sort of my cartoon talking about what exactly the inside is going on. On this side, you can see is we have the anode and cathode. So we have a lithium metal anode and a sulfur cathode. And that's we are using the membrane with the electrolyte. You can see the lithium ions, the charging, discharging occurs. They move from anode to cathode and cathode to anode, depending on the case. So if you're charging, it goes from positive to negative. Discharging is coming back to positive. But the key thing is I would like you to understand is the lithium sulfide is a polysulfide system. What it means is lithium can form several intermediate compounds going from Li2S. Look at here, Li2S8. So this is the polysulfide formation, which sort of causes the degradation of the cathode. So our idea is to see if we can understand are these polysulfides are stable, and if they are stable in which phase, and what kind of mechanical property do they offer? Because if you remember, the problem with the lithium sulfide battery is this volume variation. An expectation is if we have this polysulfide formation, and if you pick up, say, the higher polysulfides, of course, it's going to be a higher volume. So can we provide a guidance to experimentalists? Can we reduce the formation of these higher order polysulfides related to lower order? So it's not going to have significant volume variation, and it's going to have a longer shelf life. That's the message. So what I said is let's look at the reaction now. So we have, again, you can see the anode and cathode, and the sulfides is coming in and out. And this is the reaction. The sulfur at the cathode here interacting with the lithium ion. And of course, we have the electrons forming a lithium sulfide. But sometimes instead of a Li2S, we have a formation of polysulfide. And this polysulfide, in a sense, has been identified as the cause of the degradation. So our idea is to understand the structural, mechanical, and electronic information about the polysulfide so that knowledge can then be used to suppress their formation and thereby increasing the shelf life. So let's look at the current state of the art. And as we all know, the Tesla is leading the pack. And if you look at the pack level versus the energy versus the kg, and this is the volume and this is the energy density, you can see it's pretty high. This is Tesla S model car gives you. This again is another sort of lithium based compound. But the idea is coming from this is going to increase both in terms of the size, smaller size, but smaller weight as well to have a better performance so that can be used for, especially in automobiles or other applications. And this increase is we expect to improve the performance by looking into the chemistry and physics of the system, the materials point of view.
So I said earlier is again repetitive is conductivity, of course, is poor, but the big problem is this polysulfide formation, especially the higher order polysulfides, which sort of dissolution, so-called, leads to a shuttle effect. And then you have loss and of course, the design of the electrodes. And this, especially this part, basically comes down to engineers. So what do we do? And the question comes down to, let's look into the design of cathode. So first thing comes down to the cathode is, as you know, we have sulfur cathode. So we had to, again, aim is to see is suppress formation of polysulfides. And once they are being formed, then they should not go to the electrolyte. They should be contained at all. So idea you can see, aha, so what we take is so-called the yolk shell structure. It's like an egg. Okay. So you have the sulfur cathode, but is again surrounded by a shell. That could be a nanotube or could be a surface coating. So that once the lithium ions comes in and they form the polysulfide, they do not come out and get dissolved in the electrolyte. The second idea is instead of having a yolk shell structure, let's pick up the nanotubes. And in this nanofiber structure, a nanotube structure, we have the carbon hollow. We simply pack our cathode sulfur material. So this is densely packed, our cathode. But so this comes from engineering point of view. What else can we do? We look into this formation process. So you got to start with some hypothesis. So what we have is this cathode is a nanostructure. And what we're saying is here is this spatial confinement, of course, is going to lead the polysulfide formation, but it's not going to get dissolved in the electrolyte. Simply this only let it go, the lithium ion, but not the polysulfides. So we look into what exactly these polysulfides are coming from our simulation. That's the key thing here, the different properties. So what you do is, this is a typical charge-discharge curve, but let's look at the right-hand side. So here we pick up a polysulfide called Li2S2, okay, lithium disulfide. So first thing you would like to know, what kind of crystal structure is stable for Li2S2. So trick of the trade is what you do, you pick up if you remember the crystal structure, we have the 7 available crystal structures. So we form a Li2S2 unit based on different crystal structures. So you can see is the unit is sulfur is in yellow and Li is in green. So we have Li2S2 unit in a tetragonal crystal structure, in a triclinic, or we have hexagon structure. So once we identify, we calculate the total energy of the system. And once you have the total energy, then we compare the total energy and the structure with the minimum total energy. What we say is going to be the most stable structure, which is going to get formed at the cathode, in the battery. So you can look at this formation energy, which is a per Li2S2 unit, and the different crystal structure. Now, yesterday I talked about it, and I'll talk more about tomorrow, is our reliability or accuracy of DFT calculation depends on what kind of functional form we use. So if I look at this called the GGA form, I find, aha, my tetragonal structure is the ground state, but triclinic and hexagonal are about 700 or 1/10 EV higher. So this set of calculation tells us that tetragonal is the lowest energy structure. But once I improve the accuracy of the modeling elements and add in so-called the van der Waals interactions, which again, coming from the chemist point of view, that as we talked about carbon-carbon bond, because of the pz orbital sort of flexible from the both sides, they had this flexible electronic cloud. So that's also valid for the sulfur-sulfur bond. So this van der Waals term can only be used to see if this does matter, if sulfur-sulfur bond requires this van der Waals type of terms. And we add it, we find is the picture is totally reversed. In this case, my hexagonal structure has a lower energy compared to triclinic or tetragonal. So this also addresses one of the questions we had, I think if I remember from Dr. Naidu, is what is the limit of DFT? What is the accuracy or reliability of DFT? So it all depends on what kind of elements, model elements you use. If you use only so-called the PBE, you have a different answer compared to what we use, which is a little more accurate in terms of the physics and chemistry of the system. So one has to be very careful, sort of your educated guesses. If I pick up a sulfur containing or carbon containing compounds, I had to have this van der Waals interaction. Simple oxide, say magnesium oxide, or in a diamond where we have a strong covalent bond, then this PB, it works very well. And I'll show you some of the examples in tomorrow's talk. So we have Li2S2. Now we thought let's do the other polysulfides. So here I'm not showing all the results because this is about 2 years of work of a PhD student in Chengguo. But this is the summary, because these are very, very extensive calculations. You have to pick up, say, for Li2S8, all sort of combinations. And you can imagine and do the total energy calculations. And then you find is which of the structure has a minimum total energy. And then you say, this is my ground state. So first thing you notice here is Li2S, as we know, is pretty standard crystal. You have LIS bond, they're dominating. We move to LIS2, we tend to feel, is the sulfur-sulfur bond is now starting to show up. But if you look at the Li2S8, so what we have is simply, you can see the layered structure. You have the sulfur layer, coming the lithium layer, and the sulfur layer. So as you expect is that when a sulfur-rich lithium compound, sulfur chains, they take over, compared to what we have in the lithium-rich case, where the LIS, which is a primarily covalent ionic bond. But for sulfur-rich, the covalent bond between sulfur takes over in governing the ground state of the material. That's the first message coming out of the calculation. And then you say, okay, let's see what is the formation energy is compared to Li2S, because this is a well-known case, monosulfide. So this is a standard a diagram referred to called convex hull. So here what you do, you pick up the monosulfide and see if you can dissociate into the lithium metal, or you have the sulfur compound. And simply you draw this hull, the convex hull. And then you plot the formation energy with respect to sulfur and lithium on this graph. And what you find is indeed all these polysulfides are between the hull, which tells us they are a metastable compound with respect to Li2S. And that's coming out very nicely. But had it been the case where all these polysulfides are either here, somewhere or way up there, then they can form a stable compound with respect to Li2S. But this is not the case. They are going to be metastable.
now look at the electronic properties. And what you find is if you look at the cubic Li2S3, so here I have not shown it. So Li2S is a semiconductor. It has a gap. Li2S2 has a gap. But if you move to Li2S3, if you can see here, is a non-stoichiometric. Hardly is a sulfur rich, but it becomes metallic. And that's very important in terms of the conductivity. And you do further analysis about what kind of bond these compounds are forming. And as I said earlier, that for polysulfides, the sulfur rich, this sulfur chains are dominant now. So they form this S2 pair. And our idea is to really analyze chemically in terms of the orbitals is what kind of composition they are going to have if the two sulfur atoms form a sulfur ligand chain. And you fill, you have these atomic 3s, 3p sort of orbitals. And when you come in and they form, they have the stable and the so-called the unoccupied or occupied states forming S2. And then from this information, what we do, we look into the distribution of the states. And I said is Li2S3 is metallic means if I look at the Fermi energy, there is no gap. Okay. If there is a gap at Fermi energy, we call it a semiconductor. But if there is no gap, there is a finite density of states. And if you remember, what is the density of states? Density of states is the number of available states for electron to move around. So if electron does not have any gap, can move around, we say this is a metal. And then you can identify the sort of a different, the orbitals in terms of this molecular orbital analysis. So this information you can see here is very useful to interpret the optical spectrum of any given compound. So what happens is here, simulation comes in, it predicts it's going to be metallic or non-metallic. And you look at the states and find out what kind of nature they have. So any optical spectroscopist then, when takes the measurement, they see these peaks and they can identify, this peak is due to sulfur, is a sigma type bond or pi bond, and so on. So simulation really provides a fine details, atomistic details of the whole compound, what exactly is going on in terms of the bond formation. And then you look into the volume versus stoichiometry. And if you remember, we talked about the volume expansion. So if I look at here, in the lithium rich, we have the lithium sulfur bond is dominating. The sulfur rich, sulfur bond is dominating. So if I use this as a reference case, okay, you can see it's more or less constant, but it moves to Li2S, there's a big jump, almost about 70% we predict. So you can see now the experimental observation is there is a volume expansion. But experiments do not know what causes this expansion. Simulation comes in and we identify is this expansion causes because of the lithium rich compounds. Or you can say the formation is pretty high here, you can the other way around. When sulfur takes over, there is change in the volume. So this sort of helps let them to understand exactly what the fine process or the atomistic process is governed in this polysulfide formation. Then once you have the volume, we'll show you tomorrow also, we can easily extract the information about the mechanical properties. And these are the bulk modulus, which is a mechanical property, the stiffness of the material. This is gamma, and this is called G. This again is characterizing how stiff, how brittle the material is in terms of it. And you can see here is Li2S,
the lithium rich being the ionic bond, has a pretty high value of these elastic constants relative to sulfur rich compounds, which sort of goes down almost from 40 to about 10 gigapascal. Okay, Dr. Naidu, so I'll explain again. Let me go back. So experimental observation is there is expansion. And expansion is due to the formation of polysulfides. But there's no information about is it lithium rich or sulfur rich polysulfides, or what is the transition point of that expansion. So we considered all the 8 formation of the crystal structures and find these are the ground states. Then we thought is, let's see these polysulfides, are they stable with respect to Li2S, or they are metastable? So we approach this convex hull diagram, which picks up the junior member or the first member of lithium sulfide compound, which dissociates into lithium and sulfur. So you combine these 3 points is the parental compound and so-called the individual compounds which it dissociates. So this gives a hull. And if the formation energy of all the compounds are within the hull is known as these compounds are metastable with respect to Li2S. So that's a good news. Okay. So once we know they are metastable, then we thought, okay, let's do and calculate the volume of these polysulfides. And you can easily calculate volume because you had information about crystal structure, A, B, C, alpha, beta, gamma in terms of the angles. And once you calculate the volume expansion, you realize is there is a drastic change in the volume as you move from lithium rich to the sulfur rich compound. So this is one of the causes. Suppose we don't know the experiment result. From this graph, we can say, indeed, a volume expansion occurs as we cross from sulfur-rich polysulfides to lithium-rich polysulfides. And this is sort of our educated guess in terms of the transition. And from there, you can talk about is how the mechanical response of how stiff or how brittle these compounds are. And we can calculate from elastic moduli. And you can see here it reflects the bonding in the nature is Li2S, we know, is dominated by Lis bond, which is ionic bond. If you look at the lithium sulfide, polysulfide, sulfur rich, we have the sulfur 2, S2, which is sort of a little weaker bond because the van der Waals terms, and they have a very, very small elastic moduli. So this again is, we can say, the mechanical response is going to increase during discharge or decrease during discharge or charging process. It's both ways. Is it okay, Dr. Naidu? Good. So I think this is incremental steps. If someone asks the question is, first say, okay, let's figure it out. What is going to be the ground state of these unknown compounds, which are being formed in a battery? Okay. So you calculate the total energy of every given system. And once you have the information about total energy, you calculate the formation energy. See what the stability is. And once you know what stability is, then you can simply calculate the volume, which is from crystal structures coming out, or you can calculate the mechanical properties. So this sort of ties up to the experimental observation, and we can interpret the data. So I think this is the last slide. There's going to be We are still doing it or some work because this is the X-ray absorption data is out there, and they are looking into the lithium polysulfide solid. And our plan is so they have this peak, absorption peak, they don't know which polysulfide sort of causes that peak. So we had to identify and again feedback loop to experiment for doing it. There's a lot of applications going on, which I hopefully talk on day 5 to show it. But you can see here, this is a very extensive work, almost 2.5 years, by one of my grad students who just graduated to look into these materials. So simulation is not easy, what I'm trying to say. It takes as much as time as we do in experiments, and they go sort of complementary to each other. So this is again just gives you an idea is where are we heading. If I look at the energy density in terms of the voltage, capacity, weight, we are somewhere here in about the lithium ion, but again is theoretical difference. Theoretical densities are coming up, and expectation is that lithium oxygen is going to be way up. But we also know that's going to be very, very reactive, which may not be possible to reach. But again, the goal is pretty good in terms of achieving the energy density of these materials. This gives you another idea about the cost. When we use the cobalt oxide as a cathode, not the lithium sulfur we're talking about. We're talking about the existing lithium batteries in our phones and so on. The anode is at least hardly any cost because the layered carbon, but basically the money or the cost is going to come from cobalt oxide, which is pretty high. And you can see the density is also about coming out about 200 to 250 watt-hour per kg, which is a decent one. So that's the end of this session. And but if I remember, Dr. Naidu asked yesterday about the list of programs. So there's a question, I think. Okay. So if you do a little Google search, and you can find the Wikipedia has a list of all the software packages. But I suggest if you would like to start, look into this program called Siesta. It's free, you can download it. Is not very, very accurate related to other programs, but it gives a decent result. And as you know, if we always are limited by the computational power we have. So Siesta can easily be run on a small laptop, at least for days or something, and you can see some of the results. And then what we have is called the post-processing software packages. If you're looking at the quantum transport, to look into this carrier mobility, either in photovoltaics or photocatalysts or some of the material, they are very, very fast. So once you have the results from Siesta, it hooks up to either called Golem or Quant. And you can use both of the programs for looking at especially the thermal part. If you are interested in thermoelectrics or electron transport. That's very nice, and again is a very helpful packages. So my approach is going to be think about it as a black box, without knowing exactly in the box is, but can I use this box? So I still always believe in learning through incremental steps, because I still remember my mother used to tell a story about Chandragupta and Chanakya. When Chandragupta lost his first war against nuns in Patna, both were running and land up in a small village, and one old lady sort of served them khichdi. And Chandragupta, being Chandragupta, he simply landed his hand into the center of the khichdi, which was very hot. And then old lady said, you are just like behaving like a Chandragupta. Why don't you start from the sides? So whenever you want to tackle the problem, it's easier to go slowly rather to the center of the problem. That's my philosophy has been. So incremental steps is slow. You're going to get frustrated, but at least by the end of the day, you're going to have an answer. And that's, you can see, proof. So this approach really helps to get into the simulation. But again, you have to have some tools. And what I say is some elementary knowledge, how to install the program on a laptop. And once you install it, you have source code, then how to compile it. Means you have to have access to compilers, which are again is freely available through Intel or some other companies. And once you compile a program to call executable code, then simply start running the calculations. And then again, you test. And the best test is you use a very simple approximation. Don't simply get into the very, very highly accurate calculation and ask the question, can I calculate the electronic structure of, say, magnesium oxide? It takes only 2 minutes. And at least you know the answer, you know the structural property, you know the band structure, density of states, effective mass, and so on. And once you have it, when you get expert in 6 months, then you can join a community, or you can move to simulation groups. In India, a lot of people are doing it. And I know one person is very, very supportive, Dr. Verma from Bhilai. Anytime you can write to him, especially he's expert in siesta. And you can say that Dr. Pandey has referred his name, and he's definitely has welcomed a lot of students in his group for a week or so to train them in running a siesta code and so on. So you said you have a question. Yes, Dr. Hinge, answer is yes. And I have not shown it here, but I should dig out the information for tomorrow's talk, because I had 3 talks about simulation, and I'll show you the Zenus and FS spectrum, which we calculated and compared with experiment. So answer is yes, but they are a little more complicated calculations. Good. Any other questions? So it'll be almost 1 o'clock. Time over. Time for training is running a little late, but I think it's worth it. So the last one is, as you know, Dr. Bhavna Singh is always up to me to provide the homework problems every day. So this is a simple one. Especially, if you look into this, is a very quick and understanding of the theoretical calculations, which provides what is the efficiency of a given material for solar absorbed in visible region. And simply it all depends on the band gap of the material. So if you do Google search, you can find, so you can understand. Someone asks, I have a material which a band gap of 1 electron volt or 3 electron volt. Would it work for photovoltaics? And you can see, again, quick answer is yes or no. That's, I like this limit, it's pretty good. This is, again, electrochemistry reaction, which is going to be helpful for tomorrow's talk. Is a hydrogen evolution reaction or oxygen evolution reaction. And this is all related to, I call the term overpotential. Again, is my idea is to provide this concept is that someone tells you, if I have an overpotential of say 5 electron volts, would it be good photocatalyst? And easily you can say no. So this gives you sort of, I call the back of the envelope calculations once you know these numbers. And same thing with the last question is, which you know the answer also. What should the range of this hydrogen binding energy if you want to store hydrogen in a given material? And should be H2, not H actually, hydrogen molecule, which we know is a weak. But if you give some numbers, I will have some idea what number we are talking about. And battery, I think we talked about this. can just have a good, provide the difference between liquid and solid. You're going to have this understanding. Great. Thank you again. And I'm still open. I'm around. If you have comments, let me know. But tomorrow is going to be a little challenging because I'm going to pick up the examples. Like think about the black box, but we'll show you especially the bulk in the first talk. Second talk, I pick up the 2D or graphene or beyond graphene. And third one is going to be on carbon nanotube and the applications. And although I know the talk is about energy related, but with the carbon nanotube work, I'm going to show you some health related results so that you have a sort of a total idea about what kind of tools we have and how can we use them. So we'll mix and match and go from there. Thank you.
Thank you so much, sir. Thank you everyone for joining us today. We are on a break right now and we will have our next session from 3:15. Till then, we are open for a few doubts and queries. I would request you all to please turn on your cameras for a photograph.
Vijay, I can show you some examples about the spectrum tomorrow. I hope you're enjoying Dr. Nagvanshi. Oh, sorry. I didn't know. I thought Durgesh Nandini, no?
Thank you, everyone. We have taken the picture.
You're counting down the seconds until you can skip the ad, right? I get it.
Good afternoon, all participants. Today, we have discussed the tutorial session about optical analysis of the nanomaterial. इसको थोड़ा सा मिनिमाइज करता हूँ मेरे से कर दूं Now we have start optical analysis of nanomaterial means basic. First we have discussed the basic phenomena of optical. Optical where the optical is just related to the light. We have discussed few जो phenomena ऑलरेडी आप लोग जानते हैं उस पर मैं डिस्कस करूंगी बहुत हाई लेवल नहीं है बट हाँ उम्मीद करती हूँ कि सबको बहुत अच्छे से समझ आएगा स्लाइड मूव नहीं हो रही okay first we discuss all are you know what is absorption emission and transmission of the light these all phenomena related to the substance when first light phenomena so many phenomena light phenomena such as reflection interference polarization diffraction but today only we have discussed what is absorption and emission what is absorption and emission इसके लिए मैं आपको ये बेसिक फिनोमिना सच एज जैसे कि जब एनी लाइट electromagnetic radiation incident on the substance or any material completely depends on the material the light is reflected which is totally depends on the surface of the material when the surface is opaque then the light is reflected such as wall any rigid surface then the light is reflected and when light is incident on transparent material the light incident on transparent material then it passes completely such as glass so this is known as transmitted light when light incident on a specific material a particular material such as sodium potassium hydrogen so some portion of light are absorbed some portion of light are absorbed means which portion the frequency matches to the particular frequency which is matches to the particle of the material which particle is absorb the energy and this wavelength is not matches the particle does not absorb the energy then it is transmitted which energy that is absorbed which is absent to the output of the transmitted light and which energy not absorbed which is find to the output that is known as absorption then after absorbing of the frequency or wavelength, this material particle is excited from ground state to higher state. Ground state to higher state, when the particle does not live and higher time in higher energy state, it is very less time, approximately 10 raised to the power minus 8 second, and comes from the higher energy state to lower energy, means ground state. It comes to the ground state. The particles emits the energy from coming from higher state to lower state. This is known as emission. Means we have basic idea about incident radiation, how it is reflected, and what it is absorbed, which frequency is absorbed. Then after absorption, what type of emission is emission? Be two types is also radiative, non-radiative, thermal, and light emission. So many. Then some portion of the light is absorbed. Then it transmitted. Then it transmitted. This is known as transmission of light. Means this slide shows the absorption, emission, and transmission of the light. Basic idea. Just we study these phenomena after emission, absorption, and transmission. We have found some outputs. Some output. We have studied particular spectroscopy. This is we have found the spectrum. This spectrum is different type. That is discussed here. There are two types of spectrum, known as continuous, discontinuous. So when light is incident, it passes through the material. So many phenomena we already discussed in previous slide. So we obtain continuous spectrum with mouse कहाँ move हो रहा है? We obtain a continuous spectrum. Continuous in so many. दैनिक जीवन में अगर हम देखें तो continuous spectrum के कई एग्जांपल्स हमको दिखते हैं, सच एज रेनबो. रेनबो में जैसा आपने देखा जो स्पेक्ट्रम होता है डेट इज कंटिन्यूअस. और जब बारिश के समय में देखते हैं कि जो रोड होती है, रोड में अगर पेट्रोल डीजल जो पानी होता है उस पर अगर आता है, तो जब ईएम रेडिएशन, लाइट रेडिएशन, सन रेडिएशन उस पर इंसिडेंट होती है, आफ्टर इमिशन रोड में हमको जो स्पेक्ट्रम दिखता है that is continuous spectrum. When we passes the light through the prism, we have find the continuous spectrum. Continuous spectrum means all 7 colors are mixed to each other, where the end of the particular wavelength and which is starting from other wavelength. It is not clearly mentioned. It's continuously mixed. That is, first is shown is continuous spectrum of the light. Second one is बोले तो emission spectrum and absorption spectrum. They both spectrum two are complementary to each other and opposite to the each other. When the light is passes through the sample, the particular wavelength of the light absorbed to the sample, it depends on the material. Which wavelength is absorbed, which is not found in output or transmitted spectrum or transmitted light. Where the wavelength is absorbed in transmitted light, we have obtained a dark line in which places, which wavelength is absorbed, which is absent in the output of the spectrum. But which wavelength, which light is not absorbed, then which is found in output spectrum is a bright spectrum. The wavelength is absorbed, in which place we have found the dark spectrum. just opposite to the emission spectrum. Then emission spectrum is where the wavelength is absorbed, in which place we have find dark bright lines, and the spectrum is not found, not emitted, not absorbed, in which place we have find dark lines. And absorbed line is bright color in, and base is dark color. Just both are opposite to each other. Means क्या हो रहा है इसमें? Basically अगर हम देखें तो जो एब्जॉर्प्शन में जो वेवलेंथ एब्जॉर्ब हो रही है, उस प्लेस पर क्या हो रहा है, वो वेवलेंथ हमको नहीं मिल रही है. नहीं मिल रही मीन्स उस वेवलेंथ के प्लेस पे क्या हो रहा है, हमको डार्क लाइंस मिल रही हैं. ओके. और इमिशन में क्या हो रहा है, इमिशन में जो वेवलेंथ एब्जॉर्ब हो चुकी है उसके जगह हमको ब्राइट लाइन मिल रही है, और जो बेस हो रहा है डार्क हो रहा है. ओके. माउस डिस्टर्ब कर रहा है. We have discussed spectrum. Spectrum is two types: continuous spectrum and discontinuous spectrum. Continuous spectrum, just we have explained in previous lecture, previous slide, rainbow, prism, and it is particular arranged in the higher wavelength to lower wavelength to higher wavelength. That is continuous spectrum. Discontinuous spectrum, the gap between two wavelength. This is known as discontinuous. Means it is found the gap between the one wavelength to another wavelength to another wavelength. That is discontinuous. It is also two types: absorption and emission spectrum. Absorption spectrum, when the light is passes through the sample. Light means white light source. Then sample absorbs something energy, some light, and it transmitted. These light are detected to the spectroscopy. Then we find the spectrum, which is an absorption spectrum. And then emission spectrum, the particle is jump from higher to lower energy state. It emits some energy. This spectrum is taken through the spectroscopy. Then we find the spectrum which is known as emission spectrum. Emission spectrum is also two types: line spectrum and band spectrum. Line spectrum is a spectrum of atomic material, atomic particles होते हैं, that is shows the line spectrum. And band spectrum is the molecular spectrum. Molecular means the number of atoms are included in this band spectrum. Band spectrum is also two types. It is higher, arranged in the higher frequency to lower frequency, and lower frequency to higher frequency. Okay. Now, basically, tutorial session, we have explained what is UV visible spectroscopy, what is absorption, and how we calculate and analysis of this absorption spectrum, which is find in the our analysis, such as energy band gap and particle size. So first of all, we have discussed in what is visible absorption spectroscopy. It is an instrument which is used in multiple field, wide range of field, not only chemistry. It is used in life science, biotechnology, biochemistry, food science, pharma. So many field it is used. How it is used? क्यों उसको यूज करते हैं? तो it shows the concentration of the molecule in the sample. So many phenomena we have obtained, energy band gap and which type of chemical bonding in present to the sample or solution. For UV visual spectroscopy, two things is more important, and one is electromagnetic radiation and other is spectroscopy. Electromagnetic radiation. So electromagnetic radiation combined the so many wavelengths such as the radio waves, microwaves, infrared waves, gamma rays, X-rays, visible light, ultraviolet lights. Electromagnetic means it combined the electric radiations, electromagnetic field, electric field and magnetic field. Electric field and magnetic field are travels in perpendicular to the each other. This is the diagram of electromagnetic radiation. It is so higher wavelength in left to right side. Higher wavelength means particular जैसे जैसे wavelength increase हो रही है, we increasing the wavelength, then a small wavelength in gamma ray and higher wavelength in radio frequencies ray. When the gamma ray means wavelength is very small, a small wavelength, then energy and frequency is very high. We have also now E equals to H nu. Nu equal to Cy lambda means frequency and wavelength is anti-proportional to the each other. Then frequency is larger, then wavelength is lower. Means energy higher, then wavelength is lower. Energy higher, frequency higher, then wavelength is lower. When the right side, the wavelength is very large, then in these waves, the energy is very low. Okay. Now, which type of spectroscopy in used for UV and visible range, which is known as absorption spectroscopy. When the EMR radiation passes through the sample and we have found the transmitted light. Then after study of these lights through spectroscopy, such as the light, this is the light. Light means electromagnetic radiation. Electromagnetic radiation passes through the sample. It absorbs some energy, then passes after to the output. These transmitted energy detect to the detector. Okay, then study this detected energy or spectrum. Spectroscopy is also two types: absorption spectroscopy and emission spectroscopy. Today we have discussed only absorption spectroscopy. What is absorption? Absorption means particle in ground state. It absorbs the photons of energy, then comes to the higher energy state. Then comes to the higher energy absorbed, then going to the higher state. This is known as absorption. When the energy is not destroyed and is not created, it is transferred to one form to another form. It rests 10 raised to the power minus 8 second in higher energy state and excited state and release the energy in a form of light and going to the comes through to the lower ground state. Then the spectrum obtained through coming from the electron or particle in lower state or ground state, the spectrum is studied through emission spectroscopy. Now which principle the spectroscopy is work. The UV visible spectroscopy works on the phenomena of absorbance and principle of Beer-Lambert law. What is Beer-Lambert law? The Beer-Lambert law is when the light is incident on the sample, it is directly proportional to the thickness of the sample and concentration of the sample. Means the concentration, when which type of sample we have taken, it is proportional to the its concentration and thickness or length of the sample. Means Beer-Lambert law is ये is absorption coefficient, absorbance of the material is A. Epsilon is molar absorbance, means proportionality constant. C is concentration and L is the length of the sample. Then Beer-Lambert law is A equal to epsilon C. L. C is concentration, L is path length of the sample. This is the I is intensity of the incident light. Then I is transmitted intensity of the light, C is concentration, and L is the length of the material or thickness of the material. Then we have discussed the working of the spectroscopy, how it is work. First of all, we have taken a lamp. Lamp is it is known as UV visible absorption spectroscopy. UV, the range of ultraviolet light is 200 to 400 nanometer, and visible range is 400 to 800 nanometer. So here we use the lamp is for UV range, hydrogen or tungsten lamp is used, and for visible lamp we use the for UV range, hydrogen and deuterium lamp is used, and visible range we use the tungsten filament. The light is incident through the slit. What is the function of the slit? The light in disperse in all direction. The slit is used to its compile and form of narrow beam. It provides a narrow and intense beam to the next direction. Then here use the slit. Slit is just collimator and other is used for the forming of the slits. Then slits provide the narrow and intense beam. Then monochromator are placed here. The inside the monochromator, the grating and prism are used. Why grating and prism are used? Prism, this bending of light means monochromatic light is incident. The prism, it converts into continuous or 7 color, disperse the wavelength. Different color, monochromatic colors mein it converts the monochromator. Or grating is also used for diffraction pattern. The grating is used for same purpose. Then the monochromatic light passes through the chamber. It can passes only one wavelength on the chamber. It can passes red color, it can passes yellow color, it can passes orange color. Both passes in same chamber. It passes through reference sample and it passes through the sample. These both are in same frequency and same wavelength, passes through the both reference sample and sample. When we have taken the reference sample and sample in the cubite same sample, then we have obtained output is intensity of reflected light I0 and I, both are same. For example, we have taken a water, means we have taken in both cubite, both sample वाटर, दोनों में अगर हमने मान लो पानी लिया, वाटर लिया, तो जो आउटपुट में जो इंटेंसिटी मिलेगी I and I0 is same, no change. But we have taken in different sample. In sample Q white and reference Q white is already put the sample, then transmitted the light through reference sample and sample, and both are detected to the detector. We have find the spectrum. These spectrum are different. When the transmitted light is I0 and transmitted light through sample is I. The ratio of I and I0 is known as transmittance. That absorbance and transmission are opposite to each other. Less transmission and more absorbance, more transmittance and higher absorbance. Means transmittance T equal to I upon I0 and absorbance is obtained through the log of opposite to the transmittance, means I0 upon R. The application of UV visible spectroscopy. Already we have discussed the visible spectroscopy is used in qualitative and quantitative analysis. The technique is used to identify the molecules, compounds in its pure state, as well as biological mixtures such as protein, nuclei, acid, chlorophylls, DNA, RNA, all are found through the qualitative analysis. And quantitative analysis, in a particular standard curve, we have find the quantity of unknown molecule in the sample. Unknown molecule की भी हम quantity or bonding or nuclear bonding which is available on the sample is find through the absorption spectroscopy. Next is energy. How to analyze through the spectroscopy? We have analyzed energy band gap. So first we have explain you what is energy band gap. And energy band gap is in semiconductor. Three types of band are available: valence band, conduction band, and forbidden energy gap. When forbidden energy gap, there is no electrons and hole or particle are present. It is completely empty in the molecules or electrons. And valence band is completely filled to the electrons. And conduction band is completely empty when room temperature or 0 degree temperature. Why we use only semiconductor material? We have in morning session, Rabin sir is already discussed. Semiconductor is a very good material for optoelectronic application. It shows the very good phenomena. Why? Its band gap. Due to its band gap. Its band gap between the conductor and insulator. Then insulator, the band gap is very higher, 5 electron volt, when we cannot conduct the electrons and holes through valence band to conduction band. And conductor, the valence band and conduction band are all to merge to each other. So some phenomena in the conductor is non-source, and valence and semiconductor, it may be when its property change for incident, the light, thermal energy, light energy, then it transfer the electrons in conduction band, excited the electron in conduction band. Then after transmission, it show the very good result, such as light emits the light, so many different phenomena. Then semiconductor is generally used in optoelectronic application due to its property. Okay, then valence band to conduction band. So we select the semiconductor for nano device or optoelectronic device, such as due to semiconductor, it is used in laser, light emitting diode, PN junction diodes. Then valence band, conduction band, the electron comes from valence band to conduction band. Which electron is going to valence band to conduction band? Particular energy which is matched to the sample or electron, they have absorbed the energy. After absorbance of energy, is going to conduction band. Going to conduction band, then it just few seconds it passes through the after valence band. From passing through higher energy state to lower energy state, it shows the transition. It is shows the different types of transition. Okay. We have discussed in nanomaterial. This band gap is differ in bulk material, nanomaterial. For bulk material, the band gap is continuous. Basically, you have now the particle size is decreased when energy band gap or forbidden gap is also increases. Why? Particle size is decreased, then energy band gap why increases? Due to reason is that band gap in nanomaterial. In bulk material, for 1 centimeter cubic, the atoms is 10 raised to the power 24. Then volume density is very large volume density. Then the energy band gap is merging to the each other. Band gap is merging from each other. Then one is the same level. One atom to another atom. The 1s through merge the 1s, 2s level merging, then 3s level merging. So many atoms in a small place. The energy level are merged to each other. Then band is continuous. So that bands are continuous, then this band gap between two atoms is very less. Then when we reduce the density of the atoms, then it is reduced in 12 atoms in 1 cubic sample. So 12 atoms, then the merging level is reduced. Merging level is reduced. Only 12 atoms के 1s energy level combine होंगे, and 2s level also combined, 3s level also combined. Levels are decreased. Then the gap between both atoms is also increases. When we also volume density is decreasing, 4 or 5 atoms in 1 centimeter cubic material, then these gap also increases. But we discuss nanomaterial, means quantum material, quantum confinement material, means the particle in confined in all direction particle are confined. Then and particle is also confined. This is we have discussed in atom reduced, only one particle, yeah, very less particle, these are also confined. Then gap is very less. Sorry, level, energy level, 1s to 1s, 2s to 2s is very reduced, very less. Then the gap of energy band gap is also increases. Merging level is very less, then these gaps are also increases. Okay, means when we increasing the band gap, then particle size is reduced. In nanometer range, particle size is less, energy band gap is higher. Okay, This is known as quantum particle or quantum confinement particle. Now, according to energy band gap, it is also two types: direct band gap and indirect band gap. Direct and indirect band gap semiconductor. When the free electron returning from conduction band to valence band, the electrons and holes are recombined. After recombination process, it is divided into two categories: direct band gap semiconductor and indirect band gap semiconductor. Direct band gap semiconductor, from this diagram we have explained, we will explain what is direct band gap semiconductor. In direct band gap semiconductor, the maxima, top of the valence band and minima of the conduction band, both are aligned in same momentum. Means जो बैलेंस बैंड का जो टॉप होता है और जो कंडक्शन बैंड का जो लोअर होता है, ये दोनों का जो मोमेंटम या वेव वेक्टर एक ही वैल्यू पर अलाइन होता है. एक ही मीन्स मोमेंटम की वैल्यू दोनों के लिए सेम रहेगी. मीन्स टॉप और ये दोनों एक ही पोजीशन पर भी अलाइन रहेंगे. मीन्स द transition from conduction band to valence band, the value of momentum is same. मीन्स अगर इस पोजीशन से भी अगर ये ट्रांसमिट हुआ, ट्रांजिशन हुआ, तो सेम पोजीशन पे बैलेंस बैंड में आएगा. यहां से हुआ तो यहां से भी सेम पोजीशन पे आया. जस्ट लाइक अपर लेवल टू लोअर लेवल ऑफ द बैलेंस बैंड, same position means does not change the value of momentum. It is found in the same wave vector. Then after transition, the light is found, the emission is found in the form of light. Light के फॉर्म में हमें emission मिलता है. It is very fast due to does not change the momentum, same momentum, just drop the light and going to the valence band. It is very fast. Then indirect band gap में the valence band and conduction band are different place. Both are not in same place. दोनों different places पर assign है. See, so first of all, the conduction band is positive side of the wave vector और मोमेंटम के पॉजिटिव साइड पर अरेंज होती है कंडक्शन बैंड. एंड देन जो बैलेंस बैंड होती है, इट इज प्लेस्ड ऑन द ओरिजिन ऑफ द मोमेंटम. ओरिजिन प्लेस पर इनडायरेक्ट बैंड गैप का जो बैलेंस बैंड होता है. फर्स्ट ऑफ ऑल, द इलेक्ट्रॉन कमिंग टू द बैलेंस बैंड टू कंडक्शन बैंड इज डज नॉट इन डायरेक्ट फॉर्म because of momentum is not same in both situations. First, the conduction band align the momentum first, then it transmits to the valence band. Means first तो पहले momentum की वैल्यू अलाइन होगी कंडक्शन बैंड में. मीन्स lower of the conduction band means and top of the valence band. So lower of the conduction band, just it going before the top of the valence band, align the value of momentum. Then after both value, valence band and conduction band, the momentum is same. Then after it transmit the light and coming to the valence band, means it is first set the momentum, then it shows the non-radiative transition. Then after it shows the radiative transition. Okay. Time is also increasing from this transition in direct band gap, and direct band gap is very fast. It is take more time compared to direct band gap semiconductor. It is just used in optoelectronic, highly used in direct band gap semiconductor in optoelectronic device such as light emitting diode, laser diode, then or it is also used in rectifier. The indirect band gap transition is used in rectifier. How to calculate energy band gap from UV visible absorption data using talk plot? Means just we have discussed what is absorption, emission, and the spectroscopy work in how much spectrum is obtained, how to it is working, and what is direct band gap, indirect band gap. Just अब हम डिस्कस करेंगे कि ये स्पेक्ट्रम मिल गया हमको, इसके बाद में हम इन वैल्यू के थ्रू क्या क्या चीज एनालिसिस कर सकते हैं. तो फर्स्ट तो एनर्जी बैंड गैप, देन पार्टिकल साइज. तो कैसे एनर्जी बैंड गैप निकालते हैं? तो टॉक प्लॉट के थ्रू वेरी एक्यूरेट एनर्जी बैंड गैप फाइंड आउट होता है. दिस इज नोन एज द टॉक इक्वेशन. टॉक इक्वेशन में अल्फा एच न्यू की पावर गामा इक्वल टू ए एच न्यू minus eg. Eg is the energy band gap, where alpha is the absorption coefficient and h is Planck constant. Nu is frequency of the incident light. A is proportionality constant. It is normally taken for one in amorphous type of material. And gamma denotes the nature of electronic transition. It is direct or indirect. When the value of gamma is 2, it shows the direct allowed transition. When the value of gamma is 1/2, it shows the indirect allowed transition. The value of gamma is 3/2, it's so direct forbidden transition. Its value is 1/3, it's so indirect forbidden transition. The basic procedure for absorption spectra, we use the direct and indirect allowed transition. We compare this torque equation in the straight line equation, y equal to mx. Then from x-axis, the coordinate of y is 0, means alpha h nu equals to 0. Then we have obtained 0 equal to a h nu minus eg. A is transferred to the left side. Then we have obtained h nu equal to eg. Eg is energy band gap, means energy band gap equal to h Planck constant, and nu is the incident frequency. From Beer-Lambert law, I naught is the incident light of, and I is the transmitted light. Then through Beer-Lambert law, I equals to I naught e to the power minus alpha L. Then I upon I0, transfer this side, 0 is left side, then e to the power minus alpha L. L is length, C is concentration, then taken the log in both sides, log I upon I0 equals to log e to the power minus alpha L. Then minus alpha L equals to log E, putting the value of log E 0.4343. Then log I naught upon I, this is the anti-proportional, then the minus sign is cancelled. Then alpha L equal to alpha L into 0.4343. This is also known as absorbance coefficient. Absorbance A equal to alpha L 0.43, then wavelength gamma. The equals to alpha equals to A upon L. Sorry, this is not gamma. No, by mistake, I write here gamma. It is not gamma. Only A equals to alpha L 0.4343. Then alpha equal to A upon L 0.4343. Then divided into 1 upon 2, this value is obtained 2.30 A upon I. Then the value is alpha equals to 2.30 absorbance unit centimeter inverse. we have now E energy E equals to H nu equals to Cy lambda, H is Planck constant. Putting the value of these parameters, Planck constant 6.625 into 10 raised to the power minus 34 joule second. Velocity of light 2.998 into 10 raised to the power 8 meter per second, and this is the absorbed incident wavelength. Then since one it is converted into the electron volt, then 1 electron volt is 1.6 into 10 raised to the power minus 19 E. Then and this convert into the electron volt. We divided this parameter to this equation. Then 1.240 into 10 raised to the power minus 6 electron volt meter per wavelength lambda. Then it is convert into nanometer. Then 1240 into 10 raised to the power minus 9 electron nanometer wavelength in nanometer. Nanometer to nanometer cancel. Then energy E equals to energy band gap E equal to 1240 upon wavelength lambda in electron volt. For we plot the graph. This is talk plot graph. We plot the graph from direct allowed transition and indirect allowed transition. So direct allowed transition H nu versus alpha H nu square, and indirect allowed transition H nu versus alpha H nu ki power 1/2. It is also discussed in previous slide. Determination of particle size through absorption spectra. How to calculate the particle size through absorption spectra. We have discussed in before how to find energy band gap through talk plot. It is direct or it is indirect. We have discussed how to obtain particle size in absorption spectrum. We have referred to method for obtain the particle size in absorption spectra. First is effective mass approximation model, and second is hyperbolic band model. In effective mass approximation model, the valence band and conduction band is considered as a parabolic. And hyperbolic band model, the valence band and conduction band is considered as hyperbolic, not parabolic. First difference. In second difference is in effective mass approximation model, when the particle size is less, the effective mass approximation model is applied, such as the crystalline size of the particle is 2 exciton Bohr, means radius of the particle is less than 2 exciton Bohr radius. The effective mass approximation model is used. When or in effective mass approximation model, the electron and holes are bound in Coulomb interaction force. In electrons and holes, the Coulomb interaction force is activated in effective mass approximation model. And hyperbolic band model, the electrons and holes are Cauchy interaction force are interact with electrons and holes. When hyperbolic band model, the crystalline size is larger than 4 exciton Bohr radius when it is applied. Okay. How to calculate the particle size through effective mass approximation model? We use this equation for calculation of the particle. R means radius of the particle. R square equal to H square upon 8 Eg dash minus Eg into 1 upon effective mass of the electron plus 1 upon effective mass of the hole. This is the equation for obtain particle size through effective mass approximation model. And this equation shows the particle size obtained through hyperbolic band model. R square equal to H square upon Eg upon 2 ME star EG dash square minus EG square. EG dash and EG is the band gap of bulk material, and EG dash is the band gap obtained through the absorption spectrum obtained through the spectroscopy of the absorption spectrum. Then we have taken, for example, CDS nanocrystal. The value of bulk material for CDS is 2.42 electron volt, and it converts into joule. Then H is Planck constant. The value of Planck constant is 6.6 into 10 raised to the power minus 34 joule second. The effective mass of CDS semiconductor for electrons is 0.2 into 9.1 into 10 raised to the power minus 31. And the effective mass of CDS particle for holes is 0.7 into 9.1 into 10 raised to the power minus 1 minus 31 kg. Using effective mass approximation model, substituting the value of this parameter, we have obtained the value is put H, E, and M. Then we have obtained through effective mass approximation model, R square equal to 2.4 into 10 raised to the power minus 18. EG dash minus 2.42. EG dash obtained through spectrum. Then the value of, for example, we have taken is the value of EG is 2.3. Then the value obtained through radius of the particle is 5.2 nanometer. That is the radius of particle. Then particle size is the diameter is just double to the radius. Then particle size is obtained 10.4 nanometer. For effective mass approximation model, after putting this value of the EG 2.3, we have calculated this model in through hyperbolic band model. The particle size is obtained is radius is obtained 5.8 or particle size is obtained 11.8 nanometer. From effective mass approximation model, the particle size is obtained 10.4 nanometer, and hyperbolic band model, the particle size is obtained 11.8 nanometer. We have explained how to find through graph the value of EG. Okay. First, we have taken different value of energy band gap for CDS and PVK polymer. For example, the wavelength is 340 electron volt, 380, 420, 440. This is the value of band gap. Absorption wavelength. Through wavelength, we obtain the formula 1240 upon lambda. Then we have find the energy gap, EG, 3.6, 3.2, 2.9. Then from both column, please see the band gap increases, wavelength is increases. Then energy band is also increases. Then particle size is band gap increases and particle size decreases. Band gap is decreases, particle size is increases. Then band gap is also decreases, particle size is increase. Means particle size and band gap is anti-proportional to particle size is small, then band gap is larger. Okay. Now we explain how to plot the talk plot through absorption spectrum. Okay, the column A and column B is obtained through the spectroscopy data. We have taken the data for CDS nanocrystals. These two columns is obtained through spectroscopy. Then we have obtained the talk plot through the. So first of all, the plot between h nu and alpha h nu square for direct band gap, and h nu versus alpha h nu की power 1/2 in indirect band gap. So we take the value of h nu. This column is h nu, and this is alpha h nu square. Then we plot the graph. This is the graph. This is direct allowed transition graph. And we plot the graph between h nu and alpha h nu की power 1/2. Insert, then select line. This is the indirect band gap transition. And we have also find from only these two columns the wavelength. Then we also divided by 1240 in wavelength, we obtain the energy band gap. Insert, then from these three graphs, we have which graph is suitable, which is completely fit, which is taken. First, basically talk plot shows the direct and indirect transition. This is direct, we have calculated and also plot, but these two methods are valid and perfect. So in three graphs, the best graph which is completely fitted, which is C is not show the absorption, then perfectly fit graph is shows the direct band gap allowed transition. So we have select this graph and another two graphs are removed. Okay, मीन्स तीनों में देख रहे हैं जो कंप्लीटली फिट है, जो प्रॉपर फिट दिख रहा है, जो सबसे अच्छा दिख रहा है, जिसमें लाइन बेस्ट फिटेड शो हो, उस ग्राफ को सेलेक्ट करते हैं. तो इन दोनों में भी हम देख रहे हैं ये इनडायरेक्ट बैंड गैप और ये डायरेक्ट बैंड गैप. मीन्स जो बेस्ट फिट ग्राफ रहेगा उसको हम लेते हैं. तो दिस इज डायरेक्ट बैंड गैप. मीन्स CDS shows the direct band gap ट्रांजिशन, डायरेक्ट बैंड गैप अलाउड ट्रांजिशन. वाकई में हमने देखा भी जो CDS इन बल्क वैल्यू और इन नैनो वैल्यू आप लोग देखोगे भी, तो जो CDS मटेरियल होता है इट शोज द डायरेक्ट ट्रांजिशन, डायरेक्ट अलाउड बैंड गैप ट्रांजिशन. वी हैव टेक द दिस प्लॉट. ओके, then after we have fitting the line, then we have obtained the value of easy. This graph in x-axis h nu, y-axis alpha h nu square. X-axis is also formatted. This is perfect graph. When we put the straight line for best fitting of the curve, the value of easy, where this line is completely fitted, is here. Here is the value of HG, energy band gap, easy. This is what is its value is its value is 2.4. .38 or 2.4. We taken the value of EG equal to 2.3. Okay, this line is completely fit to the here the value of HD equal to 3.8. Then we take the EG equal to 3.8 and obtain the value of H nu EG energy band gap through absorption spectra. Okay, thank you. Stop. Any question? Please, any question? Ask any question.
Hello, ma'am.
Madam, I have one question, madam. Hello? Hello?
हेलो हेलो अलाउ करिए ना
Hello?
क्या बोल रहे हैं?
Hello, madam.
हेलो is I'm audible sir
Yes, madam.
just repeat it sir
So
just
what
a
is the
minute,
importance of... Madam, I have one
Just a
question,
minute.
one doubt.
Yes. Yes, please ask.
Hello?
Please.
Okay, ma'am. Is it audible? Is it audible now, madam? My voice is audible now?
Yes, yes.
Madam, what is the importance of direct and indirect band gap semiconductors?
Yes, sir. Yes, sir. Very good question, sir. The direct band gap semiconductor, the transition from valence band, conduction band to valence band is directly. So light is emitted very fast.
Okay.
So very fast and take very less time. And indirect band gap, the time taken is large, and transition light is emitting less, and it is form of heat. Okay, it is generally used in rectifier, and direct band gap transistor is latest optoelectronic applications such as diode, laser, mostly uses very good direct transition.
Okay. Thank you, madam.
Okay, sir. Any questions, sir?
Hello, ma'am.
Yes, sir.
Ma'am, what type of solvent used in UV spectroscopy?
Yes, sir. What type of?
What type of solvent we can use in UV spectroscopy?
Solvent, sir. It is used on the sample. Which type of sample we have taken? Okay.
मैम जैसे कि हमारा जो पार्टी नैनो पार्टिकल है वो सॉल्वेंट में डिस्पर्स होने चाहिए या कंप्लीटली सॉल्युबल होने चाहिए यूवी करवाने के लिए?
डिस्पर्स होने चाहिए या कंप्लीटली
डिसॉल्व होने चाहिए सॉल्वेंट के अंदर?
सर ये तो मटेरियल पर डिपेंड करेगा सर, आपका जो भी रिसर्च वर्क है उस रिसर्च वर्क में जो भी है डिजोल्व भी हो सकता है, नहीं वो तो उसकी केमिकल बॉन्डिंग और प्रॉपर्टी पर डिपेंड करेगा सर. देन वी हैव टेक द एब्जॉर्प्शन स्पेक्ट्रा. Okay, फिर after absorption spectrum we have study of this spectrum, then we have find how wavelength or energy it has absorbed, which is depends on the material. Okay, sir?
Okay.
And other questions, sir? Yes. Any question, please? I have. Okay. Now, thank you, please. Now, any question, please mail me, and I have completely solved this problem we were through mail.
किसने नहीं दिया? Hello? Hello? Is I'm audible?
Yes, madam.
Is there any question? Please write your question or queries in chat box. Madam is here. She definitely she will solve your questions. As a course coordinator, I would like to say very thankful to Dr. Durgesh Nandini Madam for presenting such a nice and descriptive presentation here. So I'm very grateful and thankful to Madam. Thank you, Madam. Tomorrow's session will be start by 10:30, and tomorrow we have 3 lecture session by Dr. Pandey sir and followed by tutorial with Dr. Jaydev. Thank you. Have a nice day.